So, what's our plan?
А мы будем пользоваться компьютером?
Today, I think we will go without computers, but next time we will use computers. I think like this. So today I would like to cover indigeneity problem. The problem with indigeneity is that my personal point of view is not mainstream point of view. I believe that you can't solve it. So my point of view is that in general you can solve indigeneity problem, and it's better to know not to solve it, but modern econometrics is about solving indigeneity problem. And next week, or sorry, not next week we have a big holiday. Yeah. We have a big holiday, and the week after next week we will work with panel data. So that's our plan. Today, indigeneity problem. Okay, my point of view here is that we can solve it in general. It's a very extremely rare case when it can be solved. So what it is, I will speak about a very simple scenario. So first, and panel data is just a plan, what we will do half a month later. Okay, so indigeneity problem, formal definitions as the following. Exogenous regressors. What does it mean? Exogenous regressor. It means expected value of error term given x is 0. Endogenous regressor. Endogenous regressor is a regressor, let's say x will exogenous, and W will be endogenous. Endogenous means expected value of u given W is not 0. So that's a formal definition. What happens when we have endogenous regressors? How this happens, and what can we do with indigeneity? So let's consider the following example. Imagine that
Снимать придется.
Думаешь, второй дубль? С каскадерами? Коронавирус?
Первый зараженный
в Москве. Чихаешь и говоришь, коронавирус проклятый. Так, okay, example. Let's imagine that your result on econometrics depends on the number of chachapuris eaten, yeah, plus random term. Okay, so this is your metrics final result. This is the number of hachapuri eaten. Hachapuri eaten, and this is random noise. Okay, random noise. Okay, so that's the model. And imagine that we have a random sample. So what are the assumptions? Random sample. That means x5 is independent of x3. Or what does it mean, random sample? That means xui is independent of xj if j, if e is not equal to j. So data for different people, for different guys are independent, identically distributed. So these are identically distributed. Imagine also distributed. Imagine also that we have no indigeneity problem. Imagine that expected value of u of this error term given x is 0. So if you know the number of hachipuris eaten, so basically you cannot predict beta y than beta times x. So this error term is unpredictable. What does it mean basically? If you know x, so what was the meaning of this equation? If you know x, you cannot predict u. Okay? So basically, what does it mean? It means that if you know x, the best prediction of u, the best point prediction of u is 0. Okay? So basically, it follows that expected value of y given x is, I just plug in y, expected value of beta x plus u given x, and it is
Beta x.
yeah, if you know x, beta is a constant, so you know the first term. So the best prediction of this sum is first term plus 0. Okay? So basically, exogeneity assumption says that this part of a formula is a, so what is the meaning in plain words? In plain words, exogeneity assumption says that y is decomposed into two parts. The first part can be perfectly predicted if you know x, and the second part cannot be predicted if you know x. Okay? So the exogeneity assumption says that the beta times x is the best prediction of y if all you know is x. Okay? But imagine that we do not observe x. Imagine that we do not observe x. I observe results on econometrics. So I observe what I observe. I observe y1, y2, yn. And I ask everyone, how many hachipuri have you eaten during past year? Okay? Felix, how many hachipuris have you eaten during past year?
200.
200, yeah? But you know, Felix can exaggerate, yeah? If you ask him about, I don't know, what is it? So, Felix likes to exaggerate. So what he says is it's not a true x. So, I know that, I don't know, the result of Felix is 100, yeah, it's the result in mathematics. So, and x1 star, so we do not observe x directly. We just ask every guy, what is, how many hachipuri have you eaten during last year? Okay? Tanya, how many hachipuris have you eaten during last year? 300. So we do not observe x. X is self-reported. So what we observe is x plus another random error. Let's say not u, but let's say w. No, w is endogenous regressor.
Epsilon.
Yeah, epsilon. Okay. So what we observe, so this is real number of hachipuris eaten, real number of hachipuris eaten, and this is reported, declared number of hachipuris eaten. So this is observed. So we can ask everyone, and this is unobservable. So, and let's imagine that on average, if Felix has exaggerated, that doesn't mean that someone else will exaggerate. So there are guys who don't like to declare that the true amount of hachipuris was 1000, and they just say a little bit less. Okay. So for someone epsilon is positive, for another person epsilon is negative. So, and let's imagine that on average people are fair. So let's imagine that expected value of so let's imagine that on average people do not exaggerate, do not decrease special. So on average, yeah. So this is on average, and let's imagine that epsilon y is independent of x. Epsilon is independent of u. So imagine that the only problem with our data set is that we observe a noised version of x. And in this case, what will happen if we will do simple regression? So my question is the following. So my first question. What is the expected value of u given x star? So x star, is it exogenous or endogenous regressor? So under this classification, is this x star endogenous or exogenous regressor? And my next topic, what will happen? So my next question, what will happen if I basically just, I have no x, I have I don't see this unobservable x. And so my question, what would happen? So if I estimate regression of y, I estimate regression of y on x observable, yeah, not on true x, but on observable version of x, okay? So I would like to use true version, true number of Khachapuri-Seton, but I don't believe Felix. Yeah? Yeah, look at Felix. He's smiling, yeah. 200 is close, but it's not the true value of Khachapuri-Seton, okay? So it's x star, not x. And so what happens, what I mean? I mean, imagine that I have a lot of data, that I have asked a lot of students. So my question is, I estimate y hat like beta hat times x star. So that's not true value of x. That's observed, noisy version of x. And my question is, in mathematical terms, if I have a lot of data, what will be approximate value of beta hat?
Beta?
No. Yeah, there's a problem with homogeneity. This will not be beta, because this assumption of exogeneity is crucial to have a good limit.
Mm-hmm.
So no, it will not be beta. That's the answer, but we will find it. So that's a problem.
So it won't be consistent.
Yeah, it won't be consistent, exactly. We will prove it in a moment. But first, let's go step by step. So first, we will classify regressors into exogenous and endogenous. X itself, the true but unobservable number of Khachapuri-Seton, is it exogenous or endogenous?
Exogenous?
Exogenous, because if expected value of error term given x is 0, and it's given, then this regressor is called exogenous. Okay? So x, the true number of Khachapuri-Seton, is exogenous. But if I calculate expected value of error terms given observed number of reported number of Khachapuri sitting, not the true number of Khachapuri sitting, but reported number of
It's
Khachapuri sitting.
endogenous.
Yeah, let's calculate it, and it will be endogenous. But let's check it. Don't believe me, because it's math. It's mathematics. We can check, and it will happen that it's not exogenous; it's endogenous. So let's calculate it. So what is xi? Xi
Which is the row?
Спасибо. Xi is if you look at this expression, xi is x star minus epsilon. Okay. So I just plug in everything in my regression. Yeah. So y is beta times x star minus epsilon plus u, and it's equal to so y is equal to beta times x star plus
Some gamma.
maybe it's maybe no, just a moment, let's be careful because the problem is very subtle. Yeah, okay. Yeah, just be careful. That's everything is correct, but we need to be extremely careful for the moment. So everything is correct, but that's important to be extremely careful now. Okay, so I just open the bracket. It's very easy. So I have ui minus beta times epsilon y. Okay? Yeah. So if I consider the estimated model, if I use x star is a regressor, so in this model, the error term, so let's write it once again, because the problem here is that we redefine error term. So for this model, what is error term? Error term. Maybe it's better to write endogeneity condition like let's write it like in words maybe. X is exogenous if expected value of error term given x is 0, W is endogenous if expected value of error term given W is not 0. Maybe it's better because in two regressions error term is different. In first regression the error term is this guy, and in second regression error term is which one?
In brackets.
Yeah, in brackets. So it's better to write, just be careful because the notion of error term changes. And if I just plainly check expected value of u given x bar, it will be 0. But it's better to write expected value of error term given regressor is 0. That condition is called exogeneity. And if expected value of error term given regressor is not 0, then the regressor is called endogenous. Okay, in this model, oops, sorry, I have star. I forgot star. Yeah, okay. Is it okay? Because everyone is silent. I don't know whether it's too complex. So that's okay. I just forgot star, but no one. But no one pointed that out. Okay, so this is error term. This is error term. This in brackets error term. So if I just calculate even covariance of u minus beta epsilon with my regressor. Who is regressor? Regressor is x star. Regressor is x star plus epsilon y. And I see that error term and predictor, regressor, are correlated because I have epsilon y here and epsilon y on the right hand side. And so this covariance is minus beta times variance of epsilon y. And so it's not zero. And if covariance of two variables is not zero, then expected value is also non-zero. Okay, so it follows that expected value of u I minus beta epsilon y given x star is not zero. So x star is endogenous. Okay? So basically, to check whether regressor is called endogenous or exogenous, we check the correlation or covariance between error term and regressor. Okay? Now, what's the problem? Okay, his name is endogenous. He is called endogenous. But what's the problem? We do not discriminate regressors based on the name. Yeah? Why it's a bad feature to be correlated with error term? Why it's a bad feature? Okay, let's calculate this probability limit. So we will just calculate probability limit and we'll see, booms, it does not equal to beta. Okay, let's check. Let's calculate probability limit. Okay, so first answer, x star is endogenous. So regressors are classified into endogenous and exogenous. Okay, second question. We will calculate the probability limit when n tends to infinity of beta hat. If I have this model, or that formula for predictions. Who remembers the formula for beta hat? What is the formula for beta hat for such a simple model? We have already used it.
Sum of x square
probability limit n tends to infinity. What happens in numerator and denominator? Maybe let's Google. Yeah, you may Google, or you have a woman near you, so you don't need Google.
Sum of x divided by sum of x squared.
Sum of what?
Of x times.
You have only y on that star.
Ну, снизу точно сумма x квадрат.
Okay, in denominator sum of x star squared, y star,
Yes.
because the regressor is x star. Reported x, not true x. You do not observe true x. You can't do regression on true x. Okay, and in denominator, y.
No.
Mm-mm.
Oh, x multiplied by y.
Yeah,
Yes.
but x star.
Yes, x star.
Because you do not observe true x. True number of Khachapuris either is unknown. Only observable self-reported number of Khachapuri is okay. So now let's go on. How to calculate probability limit? I think we have already done it. Yeah? Yes, no?
First of all, we can divide by the x by x star. First
No.
of all.
We can.
Because it's sum.
It's a sum.
It's a sum,
Yeah.
not a multiplication. It's sum.
Yeah, the problem is that we cannot divide by x star because we have
It's
x1
yes,
star
it's sum,
y1
because
plus
it's sum, yes.
x2 star y2
Yeah,
and here is x1 star
yes.
squared plus x2 star squared. No, they are
Unfortunately.
different. You cannot
Yes,
divide
yes.
by. No. But we can divide by n. We can divide by n in numerator and in denominator. And we have a strong law, weak law of large numbers is sufficient. We have also strong law, but for this task, the weak law of large number is sufficient. weak law of large numbers basically says that if you have random sample, if observations are independent and taken from the same distribution, so if you have random sample, and if you calculate a big sum and divide it over number of observations, this averaged observed value tends to
Dispersion.
Средняя.
Yeah. If you have random sample, then if you calculate the sum from I from 1 to n of some elephants, divided by the number of elephants, this tends to probability limit when ends to infinity. When you take a lot of elephants and you divide by the number of elephants, then you obtain expected value of the
Expected
sample
of
mean.
elephants.
So this is sample mean. So sample mean tends to expected value. Yeah. Sample mean. So if you, let's say, take 1,000 randomly chosen persons from, let's say, Moscow, and you calculate the average height, of 1,000 randomly chosen person in Moscow, then basically you obtain the mean value of height in Moscow, okay, the expected value. So basically you obtain the expected okay. So
in this case
average,
also the probability of each elephant is 1 divided by n, right? Because expected value is the probability multiplied by the some value.
if
and
the
if we take
distribution, if you speak about finite,
now I'd like to speak about infinity because it's integral in general. And that's why the probability multiplied by the value, and in this case we have the probability equal to 1 divided by n, right? For each observation. And because we have infinite number, the n tends to infinity, it's roughly equal to the probability of each observation, right?
So that's not a honest proof of weak law of large numbers. But the intuition is roughly like this. If you just pick 2 persons at random at Moscow, you take average. So the average of 2 persons height randomly selected may not be equal to the average height of a person in Moscow. But if you pick a big number, let's say 1 million randomly selected persons in Moscow, then it will tend to expected value of okay. Now, let's calculate this probability limit. Let's do it. Let's do it. Okay. It is, so I calculate probability limit. What is in nominator?
X, Y average.
X,
Y bar.
X, Y star times what? Times this term. Okay? Times beta X, Y star. Or maybe it's better to replace X. So I will go to basically to X. It's better to go to basically to X. So I will have a sum of X plus epsilon. This is X star. Reported value of reported number of Khachipuris eaten is equal to real number of Khachipuris eaten plus plus some error you are reporting. Either you add some numbers to appear strong in Khachipuris field, or either you are too shy to say the true number of Khachipuris you have eaten. So it depends. Okay, times what? Times beta xy plus uy, this is y, divided by sum of xi plus epsilon y squared. Okay? And we divide by n here and there. Okay? Let's simplify a little bit. So it will be I'm too lazy to do honestly. Oh, that's okay. Yeah, let's do it honestly. Yeah, fine. Let's do it honestly. So if I open the brackets, I will have probability limit. I will have 4 terms in nominator and 3 terms in denominator. So let's calculate them. So it will be sum of xy divided over n plus 2 sum of xy epsilon y divided by n plus sum of epsilon y squared divided by n. Okay? So this is the sum in denominator. Okay? What are the 4 terms in nominator? What are the 4 terms in nominator? But be brave, just open the bracket.
First, second, third, and fourth.
Are you sure that they are not fourth, second?
Beta sum x xa squared.
Beta sum of
Yes.
xa squared over n plus this times that.
Sum
Sum
of them of multiplication.
y over n plus that times this.
Also,
Sum of epsilon y times n. And the last one,
beta out of the sum. Also,
beta sum of these two.
yes.
Okay? Yeah. So let's calculate. So we know, according to weak law of large numbers, if we need to calculate probability limit, we just need to take expected value. Okay? Yeah. So let's take expected value of every term. So there are a lot of terms, but they are more or less easy. So there are a lot of terms, but they are more or less easy. First, let's start with probability limit of sum of xy squared over n. So according to our theorem, the probability limit of these terms, sum of elephants divided by n, in case of random sample, we obtain
Expected value of x squared.
expected value of, let's say, of x1 squared.
Yeah.
It doesn't matter. You may plug in x2, x3, x4. Yeah, any questions? This is tough? Easy? Yeah, it's better to ask.
Why it doesn't matter? It's one.
Because they are random and they have so what is x1 squared? Is the number of chachipuris eaten by a first randomly chosen person.
Yeah.
What is x2 squared? Is the number of chachipuris eaten by the second randomly chosen person. Obviously, x1 squared and x2 squared in general are not equal.
Yeah.
But according to
But
the law of it comes.
expected value are equal. If you pick up the first person, so you close your eyes, you go, what is the number of chachipuris eaten? Maybe the first person will say 200s or 500s or 1 hachapuri eaten, yeah? So this is expected value of the first report.
But it works in case of only big numbers, because in this case they balance each other.
Yeah, so it's expected value. Yeah, probability limit, expected value. So for they are not equal, but expected values are equal. So. Okay, what is probability? That's very easy. Sum of epsilon y squared divided over n. We have this term there. Who can guess? Not epsilon, but
E of
E of, who is elephant here?
epsilon squared.
Yeah. Epsilon 1, or you may say epsilon 7 squared, that doesn't matter. You can change the index because epsilon 1 is the error term for the first randomly observed person. But on average, results for the first observed person have this, are the same than average results for the second person. Okay, let's go on. What is the probability limit of sum of x, y, u over n? Who can guess? What is an elephant here? But be brave. It's very easy.
It looks like expected value. Xi
X 1 times
U1.
u1. Okay, but we can simplify because in our assumptions x, u, and epsilon are independent. If you know the number of Khachapuri-Sitten, you cannot predict the reporting error. You cannot predict the error in the econometrics result. So they are independent. So for independent variables, it's just the product of expected values. And what is the expected value of u1?
It's 0.
It's 0. And this expected value is positive, negative, 0, this or that.
Positive.
Or that.
First one positive.
And second one?
Second one 0.
Why 0? Expected value of something positive.
Positive.
Expected value, if you have a hedgehog but squared, it's on average, this expected value is
Positive.
positive. Because hedgehog may be negative, hedgehog may be positive, hedgehog may be 0. But hedgehog squared, for non-degenerate random variable, it will be positive or 0. If you take expected values, positive. Okay? Hedgehog may be positive, negative, hedgehog squared may be positive or 0. In the worst case, expected value on average, this is 0. Okay, so this is positive, this is positive. Let's go on. We have already this term we have, that term we have, that we have. I'm sorry, not yet. X epsilon. What is the probability limit of sum x times epsilon divided over n?
It's like the same like previous.
Yeah, it's expected value of x1 times epsilon 1. They are independent according to our assumptions. So it's expected value of x1 times expected value of epsilon 1, and it's 0. Okay? So we can simplify this sum. What we have in... And the last term, we have also that one, sorry. We need also probability limit of sum epsilon I times ui divided by n. So who can guess the answer?
0.
Yeah, it's expected value of epsilon 1 times u1, but they are independent. So it's expected value of epsilon 1 times expected value of u1 in 0. Okay, so what remains in our big sum? Among the 4 terms in nominator, who is the only survivor?
First 2.
Yeah, first term is beta times expected value of x1 squared in denominator. Who is survivor?
The first one also.
The first one and the last one. Okay? So it's expected value of x1 squared plus expected value of, I think, epsilon 1 squared. It's beta times expected value of x1 squared divided by expected value of x1 squared plus expected value of epsilon 1 squared. And basically, we see that this term is 0 or not 0. Oh, sorry, beta or not beta. Sorry, not 0. We have calculated, if you remember, we have calculated probability limit when n is very big of calculated, and we have obtained this result. Beta times a fraction times a ratio. So when an estimator is called consistent, not sufficient, sufficient is statistic.
When it equals to beta.
Yeah, when probability limit is equal to beta. In our case, is this beta? Is this bigger than beta? Imagine that beta is positive, but
Bigger than beta, maybe.
if beta is
If they are
positive,
positive.
no, this is something positive, like 7. This is like the same positive number, like 7. This is another positive number, like 2. So it's 7 divided by 7 plus 2.
Ah.
Which
But it's positive, it's not negative. It's not, well, it may be smaller, but it's positive definitely.
yeah. So this number, this
It's
ratio,
less than 1.
is between, so this ratio
Is
is
less
between
than
0 and 1.
Yeah.
Okay? So we see that the probability limit we have calculated is not beta. Okay? Because it's beta multiplied by something that is not 1. It's less than 1. Okay?
So it's smaller than beta, then it's
If
like...
beta is positive, then it's small. If beta is negative, it's greater.
So it's between 0 and beta, yeah?
Yeah, it's between 0 and beta for positive beta, or between beta and 0 if beta is negative. Okay, yeah. So, in our case, we see why endogeneity is bad. Because even when you have a lot of observations, you can interpret your regression like, so you have obtained beta, but this beta is not the influence. So just so that's the problem with mainstream and me. The problem is that mainstream econometrists, they say, oh, we are interested in influence of true number of Khachipuris. We are interested in causal effects, and obviously that the true number of Khachipuris eaten. So what is?
If you want to know true numbers Khachipuri, you should go to Seder.
Yeah, probably. So what is the moral of the story? So what is possible, what is not possible? Mainstream econometrics. Listen, beta hat tends to beta times some ratio, that this ratio is between 0 and 1. So mainstream econometrics, they say, you cannot, so you are unlucky, you cannot say that if you eat 1 Khachipuri more, this beta hat does not reflect your gain in econometrics result. Okay? So why this beta hat is bad? Because you eat 1 Khachipuri more, x plus 1, but y will grow by beta, and your beta hat is far from beta even if the number of observations is very big. Okay, and mainstream econometrics, it's a tradition to say, yeah, this beta hat doesn't measure the causal effect, because if you eat 1 Khachipuri more, y on average will go up by beta, and your beta hat tends not to beta, but to beta multiplied by some correction factor. Okay? So you cannot interpret beta hat like an effect of 1 more Khachipuri eaten. Okay? So you cannot make decisions. So let's imagine you are ready to pay, I don't know how much for 1 point plus in econometrics result, and you are solving investment problem, whether it's worth to go and buy Khachipuri. Okay? Yeah. So to know, to make decisions, you need to know the effect of x on y. And so mainstream econometrists are very sad that beta hat that we have obtained has nothing to do with beta. Not nothing, but it's not beta. And if x, true number of Khachapuri-Sitten, is increased by 1, causal effect is beta, and beta hat is far from beta. Okay? And my point of view, and not only mine, but that you just need to be honest about beta hat. What is the use of beta hat? Beta hat can be used when you compare two guys, and one guy says, so what is it? So, predictive. So no causal interpretation for beta hat. No causal interpretation. But my point of view that nevertheless beta hat has a predictive explanation. So what is the predictive explanation of beta hat? So if I compare two guys, one guy says me, I have eaten 200 Khachapuri. And another person says, and I have eaten 300 Khachapuri. Okay? Okay, these are not true Khachapuri-Sitten. Okay? These are reported Khachapuris eaten. Okay? But I may predict the effect, the difference in results. Yeah? So I may say that my prediction for these two persons differs. So my prediction, so y hat prediction minus y hat j, I can predict the difference of results of these two persons. That it will be beta hat times minus 100. Okay? So it's not causal effect. Yeah? It's not causal effect. You cannot exploit it. You cannot use it to influence the future. So you cannot, I need just to declare that I have eaten 1,000 Khachapuris and my final econometrics result will go up to infinity. No, you cannot use it for causal influence. But you can use it for prediction. Like if you have a lot of people with umbrellas, you see, you get up and you see a lot of guys with umbrellas in the street, you can predict that probably there is a rain. Yeah? Probably they are just strange guys who like to go with umbrellas with no rain. But normally when you look outside and you see a lot of guys with umbrellas, you can predict that there is a rain. That's obviously not a causal effect. If you send 100 guys outside with umbrellas, you will not provoke the rain. But anyway, seeing umbrella in the street is a good predictor for rain. Okay? So mainstream econometrists, they are too often, at my point of view, concerned with causal effect. Yeah, it's good to know the causal effect, but let's be happy with predictive power. Okay? So our beta hat has predictive interpretation, but it's not causal interpretation. Okay? Boom. How much time do we have? Oh, we have a lot of time.
And
yeah.
So we just is there any method which helps us to understand
Causal effect.
Yeah.
Yeah, there is method, but I don't believe it's very useful. So many econometrists, they believe that it's a very powerful method, but from my point of view, it's very difficult to use it in real application. So what is the solution for solution for endogeneity with solution for endogeneity problem. So it's called two-step least squares. Two-step least squares, or instrumental variables. Instrumental variable least squares. What is this solution? So once again, imagine that you have the following setup. You have y that is equal to beta times w plus mu I. And imagine that you have endogeneity problem. Once again, what does it mean, endogeneity problem? Expected value of this error term given your regressor is
not equal to 0.
Not equal to 0. So you have endogeneity problem. Once again, why it's a problem? Because when you will use ordinary regression, beta hat OLS, even if you have a lot of observations, you will not obtain beta. What's the problem with endogeneity? Because it seems, okay, there's some condition for expected value. Why this condition for expected value is a bad condition? Because it follows from this condition that probability limit of simple estimator is not the true value we'd like to estimate. Everyone is here, or we need to wait a little bit? Yeah? Okay, so the proposed solution, and so that's my personal view, but I'm in minority, I think, in modern econometrics. The point, so the mainstream is you need to find, I don't know whether maybe you can ask your grandma, or maybe you can go and download from root tracker, I don't know where to find, but modern econometrics says you need to find a special variable z such that. So modern econometrics says you need to find a special variable that's called instrumental variable. That is something like your regressor, but not related to your error term. So you need to find a special variable with two properties. First property, that it's, so the problem you have, these two random variables are linked, they are dependent. So the best prediction of nu given w is not 0, so they are linked. And you need to find a very strange random variable z that is not linked with error term, but linked with w. In mathematical terms, that means expected value of nu given z is 0, but expected value of w given z is not 0. So you need to find a very strange random variable that cannot predict error term, but can predict your bad regressor. Okay? And you understand that's very difficult, because these two w and nu are related, and you need to find something that is not related to w, or not related to nu, but related to w. If you are very creative and ingenious, sometimes you may find such a variable, but that's very difficult. My point of view, in this situation, that's impossible. but many believe that they have found good instruments.
And is there any like examples of such variables?
Yeah, let's provide an example for this particular case. For some simple cases, we can provide examples. But I'm too skeptical about this idea. Maybe I'm not the right person to talk about. So I understand the theory, but my point of view, that's very limited. Okay, so example in our case. Imagine that we do a very strange thing in our previous example. Do you remember? We have econometrics result for each student. Yeah? We ask each student about the number of chachipuris eaten. Yeah? And this reported number of chachipuris eaten is not the true number of chachipuris eaten. Okay? Yeah? And imagine that we ask a neighbor. So imagine that we ask a neighbor, who is sitting near you, about the number of chachipuris you have eaten. Okay? Felix, how many chachipuris Galia has eaten previous year?
I suppose 50.
50. Okay? So we have another variable. So let's check this Z eta, Zi. So it's opinion of a neighbor about the number of chachipuris eaten. Okay? So, and let's imagine that this is neighbor's opinion about the number of chachipuris eaten. So we may ask Galia, what do you think, how many chachipuris has Felix eaten?
16.
16, yeah, maybe.
Like my age.
Okay? So
we
that,
have the same problems.
yeah. So yeah, this variable has the same problems. So imagine that is, so imagine that it's basically the true number of chachipuris eaten. You may encounter, let's say, Felix in a restaurant, and if you have encountered him frequently, you can guess that he eats a lot of chachipuris. Okay? If you have never encountered him in the Khachapurna, so you can guess that he eats a small number of chachipuris. Okay? So let's imagine that Z is X plus a very big error. Okay? Plus a very big, we have U, we have nu, we have epsilon. What we have? So we need one more variable. Let's say delta. Okay? Let's imagine that basically let's imagine that variance of imagine that a very bad estimator. So this is a very bad estimator. You ask a neighbor about the number of chachipuris someone has eaten. So it's a very bad variance of this is very big. Yeah, variance of this delta is very big. But we suppose that X, delta, U, epsilon are independent. And we also suppose that on average you correctly guess the number of chachipuris eaten. So the problem is to find in real life such a variable, and let's check that these two assumptions are more or less satisfied. Okay, let's check. So I will check these two assumptions. So first, what is expected value of nu? Nu is what? Nu is let's go back to my equations, to my special case. Yeah. So in my model, let's check these two assumptions. So my model was y is equal to beta times x star plus, and their term was, who remembers, u minus beta times epsilon. Beta times epsilon. Yeah, do you remember? Okay, this was error term for feasible model because we observe only x star. Let's check. So this is error term. So, and this is our regressor. So what are the assumptions? Maybe it's better to use words and not letters. So first assumption says expected value of error term given instrument is 0. Second assumption says expected value of regressor. It's better to write roles and not symbols. Expected value of regressor given instrument is not 0. So in our case, because this notation corresponds to this case, and I have another case. Okay, so I will calculate, so I will first check first assumption, second assumption, and say, yeah, indeed, there's an instrument. And so we need to just introduce two-step least squares. So first assumption, what is expected value of uy minus beta epsilon y given what is instrument? Instrument is x plus delta. Okay? If I have information on x and delta, they are independent of u and epsilon. Okay?
Mm-hmm.
It's here. Okay? So I have information on x and delta, but my information is useless to predict u and epsilon. Okay? So I may just discard my information. Okay? And so this expected value of u minus beta epsilon and this expected value are 0, 0, 0. So the first assumption is satisfied. The next assumption, what is the expected value of x star given, so it's my regressor, given my instrument. Instrument is a number of Khachipuris reported by your neighbor, not by yourself, but by a neighbor. So x plus delta. So it's expected value of x given x plus delta plus expected value of I think epsilon given x plus delta, and the first is non-zero and the last one is 0 because epsilon, x and delta are independent. And the second condition is also satisfied. Now let's make a break and discuss what is a solution, what is called the two-step least squares. So okay, we have found a magic variable that has a, so at first that seems impossible because at first it's almost impossible. You have related w and the error term, you have related regressor and so you have regressor, error term, you have instrument. And at first you have three a little bit contradicting conditions. Regressor and error term are linked. Yeah, that's Endogeneity problem. Regressor and instrument are linked, but error term and instrument are not linked. Okay? So at first that seems impossible, but if you look carefully why it happens in our case, that we can indeed have, it seems, how can it be that that is dependent on regressor? Regressor depends on error term, but that does not depend, is not dependent with error term. How can that be? But if you look at equations, you may say, yes, there is a... So basically, in our case, regressor is composed from true numbers of Khachipuri Seton and reporting errors. Error term is u minus beta epsilon. So it's linked. We have a link between regressor and error term. This is endogeneity problem. And if we look at instrument is x plus delta. So instrument is linked with regressor, but not linked with error term. Okay? So that may happen. At first it seems impossible, but from mathematical viewpoint this is possible. You may have two independent random variables, z and w are independent. Z and nu are independent, but w depends on both of them. Okay? So at first it seems impossible. How? These two random variables are independent, but there is a... That's a little bit difficult to draw dependency with Euler's diagram. Basically, that discovers the structure. You have two components in regressor. One component is linked with instrument. Another component is linked with error term. And if you consider instrument, it's not linked with error term. Okay? Because every component in the instrument and every component in error term is different. So there are no same terms. And regressor just takes one term from instrument and one term from error term. So it's linked to both of them. And if such a magic happens, then we can do two-step least squares to solve endogeneity problem. Let's make a break and introduce two steps